Good morning, class. I hope you're doing well. So today we're talking about falling objects or motion influenced by gravity. By the end of this lesson, these are our lesson objectives. You should, let's get my pen in order. End of this lesson, you'll be able to describe the motions of the effects of gravity on objects in motion. Describe the motion of objects that are in free fall. Because I think free fall is one of the commonest motions that we all know the effects of. When you drop your glass, it falls and breaks. So we know free fall. So just being able to describe that motion. We'll be able to calculate position and velocity of objects in free fall, right? And our kinematics equations from last time are going to make another appearance. So before we go any further, we need to talk about gravity. I don't know how you define gravity or describe gravity, but take a second to think about what your definition of gravity is. Gravity technically is the force with which objects, or the acceleration of objects towards the center of the earth. You can think of gravity as a force, in which case it would be called a gravitational force. But in technical terms, gravity, what we think of as gravity, the 9.8 meters per second squared, or the 10 that you might know about right now, the 10 meters per second squared, is an acceleration with which all objects fall towards the center of the earth, right? So all objects on Earth or around Earth fall towards the center of the Earth with that acceleration. Now, there's so many experiments that have been done about gravity, and long ago people or scientists used to think that the bigger an object was, the faster it fell, because it had bigger mass and therefore bigger inertia. But some guy called Galileo later came and proposed something different, and it wasn't tested until these guys went to the moon and dropped a feather and a hammer. On Earth here, because of air resistance, if you dropped a feather and a hammer, the hammer will fall to the ground faster than the feather, just like if you dropped a piece of paper and a ball. Like one sheet of paper, you can try it on your own. If you drop a sheet of paper and you have a ball in the other hand or something, maybe a cup or glasses work very well, you can drop them at the same time and you'll see that there will be a difference in the time at which they hit the ground. But in a vacuum, and this kind of is counterintuitive, because this might make you think that because the hammer is heavier, it should fall faster, and then you can make a generalization that heavier objects fall faster. But the scientists of that day did not know about air resistance. Because of air resistance, the feather is affected more by air resistance because it's lighter. But when you take these objects to a vacuum where there is no air resistance, because there is no air, basically, there's no atmosphere, then they would fall at the same time, and this was first done on the moon. So you can pause the video right now if you think I'm lying. I mean, you don't think I'm lying, but please pause the video and then go and watch this video of the astronaut dropping a hammer and feather on the moon when they did the moon mission. The link to that video is in the description, but it's also posted on Classroom. Okay, so like I was saying earlier, scientists back in the day used to think that bigger masses fell faster than smaller masses. But Galileo went to the Leaning Tower of Pisa. I'm sure you've heard of the Leaning Tower of Pisa. Pisa, I don't know. And he dropped so many different balls at the same time, and there were spectators on the ground watching him, right? Because if he had published this without any kind of spectators, people would have thought he's making things up or that his experiments were concocted. But he did this in public so that everyone can see for themselves. Everyone could see for themselves and start rejecting these ideas that had been taught for a long time, that heavier masses fall faster. So this is Galileo and doing those experiments. So today we're going to look at these objects in free fall that are falling under the influence of gravity, and look at what the motion looks like for those objects. We looked at kinematics equations. I hope you remember them. The first one was x1 equals x0 plus average velocity times time, or final velocity, The second one was telling us that average velocity is actually equal to initial velocity plus final velocity divided by 2. And from this equation, we can also come up with the idea that because we know distance is equal to speed times time, so we can say displacement is equal to average speed, which is average velocity, times time, right? The third one was the change in displacement. No, sorry, was that the one? No, that was not the third one. The third one was V1 is equal to V0 plus acceleration times time. And the fourth one was change in displacement is equal to V0 times t plus a half a t squared. I hope you remember these equations. And the last one was V1 squared equals V0 squared plus 2 times acceleration times change in displacement. So these same exact equations, because an object in free fall, that is freely falling, is basically moving in a straight line. It's moving in a straight line just like an object that is in horizontal motion. So if it's moving in a straight line, these same kinematics equations have to apply, have to be applicable to analyze this motion. Since we know that it's moving in a vertical position with an acceleration of 9.8 meters per second squared, by the way, in case I did not clarify, the acceleration due to gravity is 9.8 meters per second squared. It varies slightly if you go to different parts of the Earth because of the elevation. Different like places on the Earth, because of elevation, it varies slightly. And in our unit 4, you will see why this variation happens. But the value that we'll use in this course is 9.8 meters per second squared, unless the question says something different. Sometimes the question says to use 10 for simplicity, but strictly we'll be using 9.8. The other thing is, normally, because an object falling downwards has an acceleration due to gravity, right, we need to choose our direction of motion. We need to choose our convention. In physics, we call it convention. Convention is basically you saying that for this question, I will choose upwards to be positive, and I will choose downwards to be negative. Or you can do it the other way around. You can say I can choose up. You can choose I choose down to be positive, and I choose up to be negative, right? So if you choose down to be negative, then your acceleration due to gravity will be negative. But if you choose down to be positive, the acceleration due to gravity will be positive. Most of the time, we choose down to be negative, and then we use a negative acceleration due to gravity. And because of that, these equations of motion, because I told you these are the same equations of motion that should apply for vertical motion. So if we just replace acceleration with g and consider down as negative, then these three equations will become v1, right, is equal to v0 plus, instead of positive a, it's going to be negative g. So this equation will be minus g times t, right? And this equation will be change in position, will be v0 t, instead of plus half at squared because of the negative a, the negative g, will be half gt squared. And this equation will be v1 squared equals v0 squared plus minus 2 times acceleration times change in displacement. Now, I know you might think, how will I know to remember to use a negative or positive? You don't have to, right? You can keep these equations as positive if you want, right? The only thing you need to remember is your convention. If your convention is that down is negative, then you need to remember to substitute the value of g as negative 9.8, right, meters per second squared. If your convention is positive, then you don't need to change the value of g. So that's the only thing that matters, your convention, because you decide. All right, let's look at an example so that you can get an idea of what I'm talking about. We're trying to calculate position and velocity of a falling object. There's a rock thrown upwards, and this example is from page 68 of your textbook. So this guy throws a rock on the edge of a high cliff straight up with an initial velocity of 13 meters per second. Initial velocity is 13 meters per second. The rock misses the edge of the cliff as it falls back to the earth, so it just keeps going down, as you can see in the picture. They want us to calculate the position and velocity of the rock at 1 second, at 2 seconds, and at 3 seconds. I'm going to start with the 1 second, at 1.00 seconds. So, since they're telling us to calculate the position and velocity at 1 second, I know they've given me the time as 1 second, right? They gave me the initial velocity as 13.0 meters per second. That's given. What else have they given me? I know it's not given, but I know that the acceleration due to gravity is 9.8 meters per second squared. And since for me I'm using down as negative, I'm going to use this as a negative value. Like I said, for you, you can use up as positive if you want, or down as negative. You just need to be consistent with what you've chosen all throughout your question. So I already have 3 things. Since I already have 3 things and I have 5 quantities unknown, I can use these 3 things to find any of the other 2 quantities, right? This question is asking me for position and velocity or final velocity. So since I already have 3 quantities, I can use an appropriate equation of motion to find any of these other 2 quantities. So I'm going to start by trying to find position. Of these 3 equations, which one can I use that has acceleration, has initial velocity, and has time? I hope you can see that the equation that I use, or that has those 3, I need displacement, it has initial velocity, it has time, it has acceleration, is that middle equation. So I'm just going to go and solve for position. I'm going to say change in displacement. So I'm going to consider this position where it started to be my vertical position of 0, right? That's my 0 position because that's where it started. And I'm even going to stop using x, and instead use y to represent vertical displacement. Y just means vertical displacement, but the equation remains the same. So change in vertical displacement is equal to initial velocity plus half times g times t squared. So change in displacement is equal to the initial velocity is 13. The time I'm interested in is 1 second. I know this acceleration is negative 9.8, so I'll do negative 9.8, half times 9.8 times 1 squared. So I'll find that my change in displacement, my change in vertical displacement using my calculator is 13 minus 4.9. 14 minus 4.9, which is, minus 4.9, which is 8.1 meters. 8.1 meters. What this means is that from this position where it was released, 1 second after it was released, its displacement has changed by 8.1 meters. So I expect it to be 8.1 meters above where it was released. So this displacement over here is 8.1 meters. What about the velocity? Let's find the velocity. So we know this is 8.1 meters. Let's try to find the velocity. The velocity of this object, again, go back here, look for what equation you can use. I want final velocity, I have initial velocity, I have acceleration, I have time. Or you can even use this one. I want final velocity, I have initial velocity, I have acceleration, and I have displacement. I'm going to use the first one because it's the easiest one. So I'm going to use the equation that says final velocity is equal to initial velocity. Instead of using positive, I'm going to say negative because my downward is negative and my acceleration is negative. So initial velocity is 13 minus acceleration due to gravity 9.8 times 1. So its velocity at that position is 13 minus 9.8, which is 3.2 meters per second. I hope you can see that this makes sense, right? Because it starts off with a velocity of 13 meters per second. But because it's going down, it has to be slowing down. And why is it slowing down? Because its acceleration is pointing in the downward direction. I hope you remember that when acceleration was pointing in the negative direction as velocity, the object was slowing down. You remember these arrows we drew? When the velocity was decreasing in that direction, that meant that the acceleration, which I'm using as blue, was in the opposite direction. So the acceleration of this object is in the opposite direction of its velocity, its initial velocity. So we expect it to be slowing down as it goes upwards. And as you can see, since acceleration due to gravity we're using as negative, it's a negative sign, the velocity has a positive sign, right? So we expect this object to be slowing down, which is consistent with the results that we have obtained. Okay, so I did that for 1 second. I want you guys to do for 2 seconds, right? And I will do the one for, actually, let me do the one for 2 seconds real quick. You will do the one for 3 seconds. So I'm going to follow the same exact process. If I want to find change in displacement, I'll say change in vertical displacement equals V naught t plus half 8t squared. Initial velocity is 13. The time is 2 seconds. I have a negative 9.8 times 2 squared. So 13 times 2 is 26, and half times 9.8 is 4.9, and I multiply that by 4. So 4.9 times 4 is 19.6. So 26 minus 19.6, yeah, hope I'm right. 0.5 times 9.8 times 4. Okay, subtract 26. I get 6.4 meters, right? 6.4 meters. So the initial one, the first, for 1 second, it was 8.1 meters above its launch point. But for the second one, it's only 6.4 meters above its launch point. It's still in the positive y direction, because that direction is positive and that direction is negative, and this is where we tell from, like this is the x-axis. So it's still in the positive y direction, but let me look at its speed. Its speed will be v naught minus or plus 80. So v naught is 13, acceleration is negative times 2, so that's 13 minus 19.6. So its velocity, I'm getting a negative value, negative 6.6 meters per second. What does that mean? Right? What does that mean? It's still in the positive, like it still has a positive displacement from its initial position, but the velocity is negative, and what that tells you is that it's going in the negative direction. And again, I hope you remember this from the graphs you drew on the Moving Man lab. I hope you remember this. This means that it's moving in a negative direction if it has a negative speed and a positive displacement. So I trust that you guys can follow the same exact steps and find the values for number 3, and then you can tell whether it's moving up or down, right, for number 3. I hope, I don't know if I talked about it, but for this one, it will be moving down because the velocity is a negative velocity, and for this one, it would still be moving up because the velocity is still positive and its displacement is still positive. This one is down because velocity is negative and displacement is positive. And I guess this one will be moving to the right. You let me know. Okay, so if we think about it deeper, what do you think would happen if the guy on the cliff throws the rock straight down instead of straight up? Right? Straight down instead of straight up. I'm going to calculate that one for the 2 seconds. So, if he throws the rock straight down, then his initial velocity is no longer positive, it's negative, because he's throwing it down, and we know down is negative. His acceleration is still negative 9.8 meters per second squared, because down is negative. Final velocity, we do not know. Change in displacement, we do not know. At time, we know the time. We know the time is 1 second, we know the time is 2 seconds, and 3 seconds. So let me calculate the one for, let me even try 1 second and see how different things look. So for 1 second, the change in displacement will be V naught t plus half 80 squared. V naught is 13 negative times 1 minus a half times 9.8 times 1 squared. So let's see what happens. I have negative 13 minus sorry about that. Someone has COVID here. Okay, negative 13 minus 4.9. It has a velocity, a change in displacement of negative 17.9 meters, right? Negative 17.9 meters. That means that when it throws it downwards, in 1 second it will have moved 17.9 meters at that initial speed. Let's check the speed. The final speed will be the initial speed plus the acceleration times the time. The initial speed is negative 13, the acceleration is negative 9.8, and the time is 1 second. So negative 13 minus 9.8, 1.8, negative 13 minus 9.8, I have 22.8 meters per second. So, and this is expected because if it had an initial speed of negative 13, right, and it accelerates downwards, that means its speed is going to increase. So that is expected. I want you to calculate the one for 2 seconds and 3 seconds. We're going to find some interesting results for the 3 seconds, right? You can let me know what you think of those results. Of course, remember, you're taking pictures of your work and turning it in. Alright, so I want you to try this one. A chunk of ice breaks off a glacier and falls 30 meters below before it hits the water. So they've given us a change in displacement in 30 meters. If you consider your downwards as negative, then this is going to be downwards because it is falling below, right? It breaks off and falls downwards. Assuming it falls freely, there's no air resistance, and most of this course there will be no air resistance. So acceleration due to gravity is also downwards, negative 9.8 meters per second squared. How long does it take to hit the water? We don't know the time, right? But we know that it starts off with a velocity of 0 meters per second, because before it breaks off, the whole thing is just stationary. We don't need its final velocity, and it's not even asked for. So we have 1, 2, 3 knowns, right? We just need to find one unknown. This is the trick for all of these kinematics problems. Find 3 knowns, use the 3 knowns to find one unknown, right? The equation that we're going to use since we want time, the equation that we shall use, again, you can go back to the equations and ask yourself, what do I have, what do I need? You have displacement, you have initial velocity, you have acceleration, and you need time, right? So since you have all of those things and you just need time, then we're using that second equation. The second equation of the ones that were there, but it's the fourth one of the equations of motion. And I told you earlier, you don't have to worry about the negatives. Just write the equation the way it is, right? Plus a half at squared. Then when you start substituting values, that's when you figure out, when to consider the negatives. I know the initial velocity is 0, so this will just be 0. I know the acceleration is negative, so I'll substitute negative 9.8 times the time. I'm interested in the time at which it hits the water. And the change in displacement, now this is a tricky one. If you just go ahead and put 30, you'll have a problem. The change in displacement is negative 30 because it falls downwards. So I have negative 30 is equal to negative 9.8 divided by 2 is 4.9 t squared. If I want to find time, I divide by negative 4.9, divide by negative 4.9. So I have t squared is equal to 30 divided by 4.9 is the same as 6.122, so many numbers. And then I'll take the square root of that answer, and I have time of 2.47 seconds. So according to significant figures, right, because this value is 2.47435, and so many other numbers, according to significant figures which you did in Unit 1, what should the significant figures of my answer be in? Or how many significant digits should my answer have? Well, since the question had a value that was 3 significant figures, I hope you can agree that this is 3 significant figures, my answer must also be in 3 significant figures. So should be 2.47 seconds. Correct to 3 significant figures because the question had 3 significant figures. Okay, one little thing I want you to do for me is get some kind of tape measure or ruler, right? Tape measure or ruler, put it like somewhere there, stand next to it, and then jump off the ground. This is you. Jump off the ground, right? Jump off the ground, whee, and then just look at how far off the ground you jump, like how high you got. Someone else can help you on this measuring device. How high you jumped. It's going to be a small value, like maybe 10 centimeters for some of you, or if you're like me, 60 centimeters. But just jump off the ground, find that change in displacement, right? It's going to be like 10 centimeters. Change it to meters, 0.1 meters. You know your initial velocity is 0. You are interested in the time that it took you to jump that height. So interested in that time. I want you to figure out your hang time. How long it takes you to reach the top and how long it takes you to come back down, right? So if you're using, your change in displacement is 10 centimeters, so you're calculating the time it takes you to get to the top. And if you multiply that time by 2, obviously I hope you can see it's the whole time that you'll be in air. So yeah, do that. Let me know what your time is, because the acceleration due to gravity is still negative 9.8 meters per second squared. So this will tell you what your hang time is. Then you can go and brag to your friends that you have an impressive hang time. And the equation you'll use is change in displacement equals v0 t plus a half 8t squared. Now just note that if you use 10 as your change in displacement or 0.1 meters, then you're simply calculating the time to get to the top. And if you want to know the total time from the down to the top and back down, then you have to multiply that little time you get by 2. Or if you want to avoid all of that, since when you go up and come down, your displacement has not changed at all, if you want to avoid all of that, just use a displacement of 0. And then if you use a displacement of 0 with this acceleration due to gravity, it should tell you your hang time. Yeah, do that and then also submit that in your work today. Your homework or practice questions, man, I must feel like I'm giving you too much work, is questions 41 to 50. Let's say odd or even. Odd or even. Let's say odd. 41 to 50 odd. Just a few questions, then page 103. Tomorrow we'll do a lab. I just wanted to ask or remind you to install the tracker software. The links were posted in the first week of class. So make sure you have that posted, installed on your computer, because that's what we'll use tomorrow. All right. Bye.